In the last video, we calculated period of the simple pendulum. This period does not change with the mass of the pendulum or angle of initial swing. Period does change with change in length. Is there any formula to find out the period of the pendulum? There is one already given in the book. Here in this formula, T is the period of the pendulum, while L is the length of the pendulum and G acceleration due to gravity. Let us validate our initial findings with the formula. Calculated values for these lengths are very close to the observed values. These differences may be due to the very basic setup, human reaction time error, etc. Mass of the pendulum does not figure out in the formula. With pi and g constant, period of the pendulum is proportional to the square root of the length. I decided to hang this pendulum to the ceiling. This will allow me to try 5 different lengths. We will start with 10 cm and increase the length 4 times, 9 times, 16 times and 25 times. As period is proportional to the square root of the length, it should be twice, thrice, 4 times and 5 times with that of the period with 10 cm length. With 10 cm, period is 0.6 seconds. With 40 cm, period is 1.2 seconds. With 90 cm, period is 2.1 second. With 160 cm, period is 2.5 seconds. And with 250 cm, period is 3.1 second. We are very close to the calculated values as per the formula. This formula is valid only for small angles. That is when amplitude is 15 degrees or less. Another important variable in the formula is g, acceleration due to gravity. We normally take the value of g as 9.8 meter per second squared, but this is average. If you perform the same experiment at sea level and at Mount Everest, you will get different readings. We cannot change the value of g locally, but there is one way out. You can use this excellent PHET simulation to understand more about the period of the pendulum. In this simulation, you can change the value of g and so many other things like length, mass, value of friction, etc. Do give it a try. Now let's discuss something about the forces on the string. When pendulum is at rest, it is said to be in equilibrium. Tension in the string is equal and opposite to the weight of the ball. But as pendulum swings, this tension also changes, as centripetal force also comes into the play. Tension is maximum at mean position, while it is minimum at extreme positions. This can be visualized with the help of a spring balance. This plastic ball is filled with sand and its mass is 100 grams. Now it reads 1 Newton. What will be the behavior of spring balance when ball is oscillating? As the ball moves to the extreme right or extreme left, the reading on the spring balance changes. It is lower at the extremes and maximum near the center. We can say that tension changes as the ball swings to and fro. Though in this case there is some change in the length as well, but we can ignore it for now. Sensors in the smartphone can be of great help. My phone has these sensors. Let us use apps like Firefox Proximity Counter to automate things for us. Counting the oscillations can be very boring over a long period. I use this app to count as well as measure time for oscillations. It uses proximity sensor available in the smartphone. When some object passes near the phone, counter in this app is incremented by 1. This plastic ball is filled with sand to make it heavy. Length of this pendulum is 35 cm. Phone is placed below the ball when it is at rest. As the ball oscillates, it will cross over the sensor. For one complete oscillation, the ball will pass twice. Let us start. It took 119 seconds for 200 counts. That means 100 oscillations, as one oscillation results in 2 counts. I also counted period for this configuration using the standard method we followed earlier. With this method, period of the pendulum is 1.19 seconds. Now that we know the formula for the period of a simple pendulum, we can use known values to calculate the value of g, which is acceleration due to gravity. In our case, period is 1.19 seconds while the length of the pendulum is 35 centimeters, that is 0.35 meters. We can replace these values in the equation and get the value of g as 9.7475 meter per second squared. This is quite close to the average value of 9.8 meter per second squared. The pendulum feature of this app can be used to calculate the value of g as well as length of the pendulum. This feature is based on accelerometer sensor. With length set to 25 cm, app can calculate the value of g, which is approximately 9.3 meter per second squared in this case. Alternatively, we can calculate the length of the pendulum assuming value of g as 9.8 meter per second squared. It comes out to be 26.32 centimeters. As this is a physical pendulum, this feature comes handy as it calculates the effective length of the pendulum. With this value now set in the initial run, the value of g is now 9.8 meter per second squared. Instead of proximity sensor, can we use light sensor? Let us use this optical stopwatch provided by the Firefox app. Light intensity is measured in lux. It can be set in this app to trigger the event. Counter is triggered when the intensity value goes below 1500 lux. We'll place the phone such that sensor is just below the ball. When the ball moves over the sensor, lux value changes as it blocks the light. Right now, we get 5 consecutive readings. We can calculate period with some simple maths. All things oscillate when pivoted at a point. This ruler with a hole on one side can be made to oscillate as well. We can attach erasers at one end of the ruler and our pendulum is ready. But can we call it a simple pendulum? Not really. It cannot be modeled as a point mass on a string with negligible weight. This is called a physical pendulum instead of simple pendulum. In case of physical pendulum, the formula for calculating the period is slightly different. You can use everyday objects instead of round ball and calculate the period as well. This small bottle is filled with sand. We can remove some sand from the bottle and change its mass. What will be the effect of removing sand on the period? Will it be the same when there is only some sand left in the bottle? Same can be tried with the help of hollow plastic ball as well. We can fill the plastic ball with sand completely and slowly drain it as it oscillates. You can also try this with water instead of sand. What happens when water drains out completely? Thank you.